negative metric, your phi is sandwiched between phi and this. And this is very interesting because if we could embed negative into L1 with some distortion at most t, then we can relate these two problems. And always think of as relaxation, because if we want to do something on a space that is much easier to deal with. And the closest things to this negative metrics is just the L1 metric. And this is known as negative type distance. And so we have a function from V into Rn, and it admits that psi of x minus psi of y squared is equal to d of x and y. So we calculate psi using SDP in polynomial time. So what we do, so we already assume that we can calculate psi using your SDP solver in polynomial time. And because this is a very easy task, so from now on we assume that we have psi because our SDP solver can do it, and so no problem. So what is their decomposition? It is they call it suites and bundles. And first we partition pi into j from 1 to n of some component containing vertex v. So let's say some components, and so it is a scale I. So when I say I, it means scale I. Remember all of the xi inside di that I told you. Di is those spaces that is their distance between 2 to the I to the I plus 1. And we define x and y is in di. We say that it is delta separated by the partition pi. If Ci of x, the cluster containing the x, is different than Ci of y. And also both x and y are far from the boundary of their components. For example, if you have x, you have y here, then and you have Ci of x, and Ci of y, then their distance from x to here. So this is, let's say this is d of x and v, excluding that cluster, and the same things for y. And this distance x and y. So, for example, we can say that d of x of v, excluding Ci of x, is greater than delta d x and y. Also, for y, the same thing. D of v and Ci of y, this is greater than delta of d of x and y. And a decomposition suite pi is a collection of these pi of partitions. So the algorithm is very easy. You project and then prune. You project and then prune. It means that you construct partitions that eta separates at least a fraction of terminals. For example, 3/4 of terminals. So you have some fraction of terminals, and eta is 4c log k. K is the number of terminals, and your input is the input of this algorithm is just your vertices and the metric d. And it's geometric representation because now we have embedded into some space that is easier. It's geometric space. It's an L2 space. It's a very geometric space. So now we project. So this is the advantages of using metric embedding. Now we project. First, the algorithm is first you project your random direction, let's say U. And then you have projection of point X that is in your embedded space onto that random partition. So you get 1 point in R, for example. 1 point in R could be represented by this. So then we create some interesting clusters. For example, first we go A0, A1, A2, A3, again A0, A1, and this goes forever. And you see that the interesting idea of this article is that this A0 is far from A0 here, and this has some interesting consequences. So in the second step of this algorithm, we bucket it. So we say that we define some length, and then beta is L of 6, and we say that our A is one of these A's. Our A's is in those of xi that P of x is in union of some intervals. For example, 4m plus a beta, and we define this interval very smartly because now the distance is it is increased by a beta. So a terminal is split by AA. If x is in AA and y is in A, for example, this is a split. First, I should say that this distance is just beta, and then we can split. And we can prove that it has some interesting properties over their distance. And the third step in this algorithm is that we prune it. It means that if there exists some terminals, for example, x in AA and y in some a plus 2 mod 4, for some a, which is a's could be 0 or 1, and we can say that, let's say, distance between them is less than this. So we can, if this happens, we just remove. Pruning is this. We just remove x and y, and of course they're partners as well from the set AA. And what is left, we do it in cleanup. So the fourth step of this algorithm says that if x and y is in B of A, and that pruning step that I talked has removed either x or y, then we remove the other one as well. And removing x and y from BA, after this is done, BA is again the set of terminal pairs split by AA and AA plus 2. So it is a split. So these pairs are split by BA. So what is interesting is that the almost last steps are 5 and 6. For example, in fifth step, we say that if the maximum between B0 and B1 is less than 1/64th of di, go back to step 1. Otherwise, you go to the next step, which says that, let's say that BA has more pairs than B1 minus A mod 2. And we define the partition by deleting all edges at distance L2 over 2F. And you should note that this procedure ensures that, so the idea of this algorithm, let's say, is that it ensures that for any pair of terminals, X and Y, for example, X is in AA, Y is in AA plus 2 mod 4, the distance between X and Y is at least L2 over F. Even if they're not, even if X and Y is not in DI. So you have your U, and you have some distribution of projected length. As I said, we project it onto that random vector, and then you get some interesting things, because first of all, this is A0, and this is A1, A2, and here the same thing, A3, A2, but A3 is enough. Most of the mass is concentrated here until A1, and that's enough, because this mass is so big, but it is less than 3 sigma, and so this is the distribution of projected edge length. So if Y falls into the light shaded interval, we can say that X and Y is a split, and with high probability it occurs, and that is interesting. And the embedding, I will show you the embedding that is very easy. So phi of X goes from V to L2. This is the embedding. And what I say is that your phi of X is just defined by these D of X and W3. This goes until D of X and W0 of I. And then the augmented with D of X 1, 1, D of X W2, 1, D of X WI 1. So this is the embedding. And of course, WI is just set of nodes contained in the cluster. For example, here is color 0 in partitioning PI. So it is just a set of nodes contained in that cluster. But it has some color. For example, color 0, it corresponds to W0, because we have a partitioning. And any pair X and Y, any pair gets a distance of delta by construction, of course, of this algorithm. It gets a distance with probability 1/2. And since the probability that, this happens because the probability that Ci of X and Ci of Y get different colors, this happens with probability 1/2. And Satish Rao, in 1990, showed that this phi has distortion of log K over delta X and Y. And you see why this log appears. And of course, this is the first embedding that you could imagine and comes to your head, but you can improve it using the James Lee approach, which is the measured descent. And James Lee modified this algorithm. So the goal is to construct an embedding in which the distance between x and y increases as local expansion v of x and y increases. I think I forgot to mention this important local expansion v of x and y. So it is defined in many papers, especially this paper, as log of b of x and 2d of x and y divided by b of x and d of x and y divided by 8. And of course log of b of y and 2d x and y divided by b of y and d of x and y over 8. And of course they proved a lemma in their paper that phi of x minus phi of y, it is related to this v. So since it is so phi is a randomized contracting embedding, so as I said, phi goes from v to L2, and this is greater than omega of v of x and y over log k alpha of x and y d of x and y. So you see how contracting it is, because this factor, it contracts the distances. And why did I say this? Because we can construct a coordinate for every t and then embed the points in this coordinate according to partitioning for that corresponding distance scale, L of t, I mean. So a pair x and y with high, let's say, very high v of x and y. So the nodes x and y will be embedded according to the partitioning for distance scale. I is log of d of x and y. That corresponds to d of x and y. So everything is like before, except we define f from v to r. First we define that, which is f of t and q of x is just the distance, just like before. But this is an improved embedding. And this wq of t is very interesting, because it says that all of your vertices, that the color of pi of lt of x is equal to 0. So this is the color of the cluster that contains this x in pi. And now, because we have defined f and tq, so we can define the general embedding. Now we can construct this, which is t times those q. And f of x is just, as you could imagine, is just f of t and q of x. So each coordinate of this embedding is contracting, and therefore all of that, I mean, the map is contracting. So because we have defined f, t, and q by this construction, now it's just is just a vector. So, and